In 3.2, our goal is to use theorems to prove the existence of extreme and average values on an interval. Let's begin with Rolle's theorem. Rolle's theorem has three criteria that must be met. First of all, f must be continuous on the closed interval. So think closed from endpoint to endpoint. We don't pick up our pencil. Differentiable on the open interval a to b. Why the open interval? Well, we can't draw a tangent line at an endpoint, so we're not looking at any endpoints. And then f of a equals f of b. That tells us that the endpoints have the same y values. The endpoints have the same y values. They're at the same level. So if those three things are met, then there must exist at least one number c in the interval a to b where f prime of c equals 0. Remember what f prime of c means. F prime means derivative, which is slope, so the slope somewhere must equal 0. So think about what that means graphically. There must be at least one location on the graph in our interval where the tangent line is horizontal, right? A slope of 0 gives us is for a horizontal line. Here's what this looks like. F is continuous, so I'm not going to pick up my pencil, and differentiable, so I'm going to make it smooth and curvy. And the endpoints have the same y values, so at whatever level on the y-axis that I start, I have to stop. So if I start here, I have to stop at that same level. So I'm going to draw a function without ever picking up my pencil, and it has to be smooth and curvy. I could have started it down here as long as I end up at the same spot when I'm done. Nothing pointy, and I have to keep drawing without picking up my pencil. I could have not made 2 turns or 3 turns. Maybe I just make 1 turn, but I stop at the same level. Maybe I don't make any turns. So here's a variety of functions. What do we notice in all of these? Continuous, I never pick up my pencil. Differentiable, it's always smooth and curvy, no sharp points, no vertical tangents, and the endpoints have the same y values. Well, in all of these, I have a max and a min. More specifically, in all of these, I can find a place at least one time where the derivative is 0. Here's a place, the slope is 0. Here's a place, the slope is 0. Here's a place, the slope is 0. This one had 3 places where that happened. Here's a place, the slope is 0. Here's a place, the slope is 0. This one had 2 places. Here, 1 place where the slope is 0. Here, an infinite amount of places where the slope is 0, because here the slope is always 0. So Rolle's theorem tells us there has to exist at least one spot on our interval where the derivative is 0. That is going to help us determine that there has to be a max or min, whether relative or absolute. It has to be a max or min because that's where the derivative is 0. And if we know it's a closed interval, our extreme value tells us, well, if the relative max or the absolute max or min is not at where the relative max or min is, it's going to be at the endpoint. So this helps us determine that there will be extreme values by telling us there has to be a place where the derivative equals 0. There has to be at least one spot where that happens. Let's look at applying it to a few different problems. Determine whether Rolle's theorem can be applied. If so, find the value of c that satisfies the conclusion of Rolle's theorem. If not, explain why not. So let's figure out whether it can be applied first by looking at the first 3 criteria. 1, is the function continuous? It's a polynomial. We need to know that means it's always continuous. We must state that. F is continuous on this closed interval. We have to state that. 2, is it differentiable? Well, it's a polynomial. We know they are smooth and curvy, so we will also say f is differentiable. And we must be specific and say where. On the open interval, -2 to 2. 3. Are the endpoints at the same level? Is f of -2 the same as f of 2? Well, let's evaluate it. -2 to the 4th minus 2 times -2 squared. What does that make? That looks like 16. And 4 times 2, so 8. So -8, so that looks like 8. And if I plug in +2, 2 to the 4th, 2 times 2 squared, and it's an even exponent, so it's not going to give me anything different there. So again, it looks like 8. So we are getting that f of -2 equals f of 2. So 1, 2, 3 criteria satisfied. So can Rolle's theorem be applied? Yes, yes it can. So we say yes, Rolle's applies. If so, find the value of c that satisfies the conclusion of the theorem. So let's write first, what is the conclusion of the theorem? So here's our conclusion. Therefore, f prime of x equals 0 for some x value on the interval let's find it. The derivative is 4x cubed minus 4x. Set it equal to 0. Looks like I can factor out a 4x. X squared minus 1 left over. Looks like I get 0, 1, and -1. All three of those values are between -2 and 2, so all three of those are the values in the interval that satisfy the theorem. Let's look at another one. Here we have g of x, 3 minus the absolute value of x minus 2. Well, I know absolute value functions tend to have sharp points. So let's check it out. Where is that going to happen here? X minus 2, set it equal to 0, x equals 2. Well, our interval, -1 to 5, includes 2. So I know that there's a sharp point at x equals 2. So thinking through my criteria, yes, absolute value functions are continuous, but they are not differentiable. So g of x is not differentiable at x equals 2. Sharp point there. Therefore, Rolle's theorem doesn't apply. How about this one? H of x equals this quotient. I see a denominator. That can often be a problem. Well, what's going on at that denominator? -2, there's some sort of discontinuity. Whether it's a vertical asymptote or a hole, it is some sort of discontinuity. The first criteria of Rolle's theorem says the function has to be continuous, but it has to be continuous on the interval. -2 is not in that interval, and we know that rational functions are continuous everywhere except at that one discontinuity. Therefore, the criteria do still apply. H of x is continuous, so we write that, on that closed interval, -1 to 3. 2, h of x is differentiable, because we know that rational functions are smooth and curvy everywhere except at their discontinuity, but our discontinuity is not in the interval, so our function's differentiable on that interval. 3, not sure yet. We've got to figure out what is h of -1, what is h of 3. Well, if we evaluate both of those, we will see that they are equal to each other. So after evaluating those, we see that they give us the same value. Therefore, Rolle's theorem applies, which means h prime of x equals 0 for some x value on our interval -1 to 3. What is it? Let's figure that out. Now we need to find the derivative. H prime of x. Well, it's a quotient. I've got to use the quotient rule. I don't believe I can factor this out. If I could, that'd be nice, but it doesn't look like I can. So denominator times the derivative of the numerator minus numerator times the derivative of the denominator over denominator squared. Remember that we're trying to figure out where does the derivative equal 0, since Rolle's theorem guarantees it happens at least one place somewhere. The denominator won't take any effect on that because the quotient will be 0 when the top is 0. So let's simplify the top. If I FOIL this and I combine like terms, I will get x squared minus 4x minus 1. That's our numerator equals 0. Okay, our numerator simplified into this. I can't factor that, so I'm going to have to use the quadratic formula. So remember quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. Yes, you still have to remember the quadratic formula. Take our a, b, and c. A is 1, b is -4, c is -1. I'm looking at these coefficients here. Therefore, x equals the negative of -4. Oh, no, sorry. I simplified this a little bit incorrectly. That's going to be 2x squared. That's going to be -2x and positive 4x, and then a positive 2x. So that's actually positive 4x right here. So b is positive 4. So -b is -4. Plus or minus the square root of b squared minus 4 times a times c all over 2 times a, or -4 plus or minus the square root of 20 all over 2, and that can be simplified because 20 has a perfect square in it. -4 plus or minus 2 root 5 over 2, and then there's a factor of 2 I can take out, so -2 plus or minus root 5. Now I'm only wanting to give the values of c that are on that interval, and -2 plus square root 5, well, that's approximately, let's see, this is close to 2, so that's going to be approximately a little bit over 2, so something like 0.1-ish, and -2 minus square root of 5, so -2, a little bit more than 2, so maybe -4.1-ish, and that one's not on the interval, so just the value of c, -2 plus square root of 5. So we're doing some estimating and giving our exact answer. Now from an AP test. Let f be a function that's differentiable on the interval from 1 to 10. If f of 2 equals -5, f of 5 equals 5, and f of 9 equals -5, which of the following must be true? Sometimes it's nice to have a little visual of the scenario. So at 2, 5, and 9, we have some positive and negative values. So let's say 2, 5, 9, -5, 5, and -5 again. So 5 and -5. So we're f of 2 equals -5, and f of 5 equals 5, and f of 9 equals -5. Now, at the beginning, they said f is a function that is differentiable. So we want to think to ourselves, we have a smooth and curvy function because I can find a derivative. I can draw a tangent line that has a slope everywhere. Has slopes, smooth and curvy. So connecting these smooth and curvy, it's going to be like this. Now, it might be that something else is happening. There might be more turns, but I know the minimum amount of work my pencil has to do is up to this point, down to this point. So which of the following must be true? Could be more than one answer. First, f has at least 2 zeros. Well, the only way to get from down here to up here is crossing the x-axis, and then to get back down, crossing the x-axis. So yes, this must be true. Do you remember what theorem that is? Intermediate value theorem. guarantees that if we go from below 0 to above 0 with a continuous function, we have to hit 0 somewhere along the way. Second, the graph of f has at least one horizontal tangent. Here it is right here, one horizontal tangent. Yes. What theorem is that? Rolle's theorem guarantees at least one horizontal tangent when the endpoints have the same y value for a continuous and differentiable function. Third, for some c between 2 and 5, f of c equals 3. Well, between 2 and 5, 3 is going to be about right here. And yes, that does have to happen because we go from -5 up to +5. So we have to hit 3 somewhere along the way. Guess what that is? Again, intermediate value theorem. So which of these must be true? All of them must be true.